So in this final video of this chapter, we are looking at weight enumerating functions. Weight enumerating functions are a specific tool to analyze the properties of a code and to derive a very nice bound on the likelihood decoding performance of a code. So what are weight enumerating functions? To start with, we take a look at our example code, the 7-4 Hamming code. And what we do is we enumerate all the code words. So we have 16 possible code words that are given by the 2 to the power of 4, 16 different information vectors, and we calculate the parity bits of those. And then what we do next is we just compute the weights of these code words, just as we would do for calculating the minimum distance. So we have the 0 code word that has weight 0. Then we have the first code word that has weight 3. We have one with weight 4. We have one with weight 3, and so on. The final one has weight 7. And then what we do is we count. So we count how many code words are of weight 3. So let's do this. We have 1, 2, 3, 4, 5, 6, 7. So we have 7 code words of weight 3. Then we have 1, 2, 3, 4, 5, 6, 7. 7 code words of weight 4. And we have 1 code word of weight 7. And then this is essentially our weight enumerator. We can write this in a more compact way, as we're going to see. So we define the weight enumerator to be a polynomial, and it's essentially the polynomial AW, which is the sum from W equals 1 to N, and AW times capital W to power W. And what is AW? AW is the number of code words of weight W. We exclude the weight 0 code words. And W is just the variable of the polynomial. So we recall our previous slide. We had A3 is equal to 7 code words of weight 3. These were the red ones. We had 7 code words of weight 3. We had 7 code words of weight 4. And we had 1 code word of weight 7. So the weight enumerator is obtained as AW is A3 times W power 3 plus A4 W power 4 plus A7 W power 7. So it's 7 times W cubed plus 7 W power 4 plus W power 7. That's the weight enumerator or the weight enumerator polynomial of a code. That's it already. So we just need to enumerate all the code words, then we count, and then we get the weight enumerator. So now the weight enumerator essentially also expresses the number of code words. So AW is the number of code words that are at distance W from one specific code word xi. So you pick a code word xi, and then the weight enumerator AW will give you all the possible code words that are at a distance of W from this code word. And that's essentially what we can get with AW. So how can we prove this? So we can prove this by using the linearity of the code. So this is only for linear codes. So what we do is we know that if we take a code word in code C, and if we add another code word, we get a new code word. So it means, in a very sloppy notation, we take a code word xi and we add c to it, we end up with c. We can take the code, we add a code word to every code word of one code word xi to every code word of c, and then the resulting set again is the code c. So now we calculate the number of code words at a distance w from xi. We calculate the cardinality of the following set, the set of all code word xj, such that the distance from xj to xi is w. So instead of going to all the code words xj from c, we go to all the code words xj from c plus xi. Because if we add xi to c, we don't change the code. So we add xj element from c plus xi, and then we look at all those code words xj such that xj plus xi is equal to w. So now, instead of going to all xj plus element from c plus xi, we can also add xi to xj. So we can go over all xj from c, then we replace xj by xj plus xi. So this is the sum over all, the set over all code words xj, such that the distance from xj plus xi to xi is equal to w. And this one is equal, so we can add xi to both sides here. That's equal to the distance from xj to the 0 vector, and that's equal to the weight. So this is equal to the distance from xj to the 0 vector, because we can remove xi from both sides, and this is equal to the weight of xj. So this is AW by definition. So AW defines the number of code words that are at a distance of W from every code word in C. And that's because of the linearity of the code. Regardless of what code word we pick, we know there are always A3 code words at distance W, or at distance 3 from this code word. So if we go back to our Hamming code, so A7 is equal to 1. So there is always one code word at distance 7 from this code word. So we can look at this one. So we know that there's one code word at distance 7. That's this one. So now let's pick for instance a code word, say this one. Now we need to find one that is at distance 7 from this code word. And then let's take a look. So it means that all the bit positions must be inverted. So let's invert all the bit positions, and that's easy because we can just look at the systematic part. So if all the bit positions are inverted, we have 1, 0, 0, 1. So it's this one. And we see that, no, that was the wrong one, 1, 0, 0, 1, this one. And we see that indeed also the parity positions are inverted. So it is at distance 7 from the other code word. And you can do the same for A4 and A3. This is just a little bit searching, but you can always find 7 code words that are at way distance 3 of a specific code word. You can find 7 code words at distance 4 of this specific code word. Okay, so now we can use the weight enumerator to calculate a very simple bound on the error probability of maximum likelihood decoding. So the bound is essentially extremely simple, and it is as follows. So we have a code C, it's a linear code with weight enumerator AW, and then we use this code to transmit over a channel C that has a binary input alphabet. So it only works with channels with binary input alphabets, and it has an output alphabet W, and the Bhattacharya parameter of the channel is B. And then the maximum likelihood decoding performance will be upper bounded by the weight enumerator evaluated at the Bhattacharya parameter of the channel. So I take this weight enumerator polynomial, plug in the Bhattacharya parameter of the channel, you get the bound on maximum likelihood decoding performance. And the technique we use to do the bound essentially is a very standard technique that is being used in communications a lot when you transmit binary values, and that relates to the Bhattacharya parameter. This is why we're going to do it in detail. So we start with the code C. So we have a code with M code word, and M is equal to 2 power k. So M is equal to 2 power k. And we assume without loss of generality that we transmit the 0 code. The proof also works with any other code word, but assume that x1 is transmitted. So now we look again at the error probability of maximum likelihood decoding, but we look at it from a slightly different direction. So the probability that the maximum likelihood decoder, which gets y as an input, that the maximum likelihood decoder decodes something different than x1, given that x1 has been transmitted, is given by the following expression. So it's equal to the sum that the maximum likelihood decoder decodes to a wrong code, that decodes to the wrong code with xj. So it's the probability that the maximum likelihood decoder decodes to x1 plus the probability that the maximum likelihood decoder decodes to x2 plus the probability that it decodes to x3, and so on and so on and so on. So it's the sum that we see here, that the maximum likelihood decoder decodes to code with xj, given that we have transmitted x1, and j is larger, strictly larger than 1. So strictly larger than 1. And we denote this to be the probability pj. And now we're looking at this very specific probability pj, and we bound the probability that the receiver decodes to pj. It goes erroneously to xj, which is pj. So how does this work? So first we define a region. So we define essentially two regions. The first region we define is the region where the maximum likelihood decoder does not decide for x1, and it decides not for x1 if there exists some xi such that the probability or the likelihood p of y given xi is larger than p of y given x1. So we have our space of received symbols, that's this guy. Let's assume this is w power n. This is the space of received symbols. And inside w power n we have a region which we call wj, and that's where p of v given xj is larger or equal, or actually is strictly larger than p of larger or equal p of v given x1. So we have this space, and in this space there exists some j such that p of v given xj is larger or equal than p of v given x1. And that's the region wj. So that is this region wj. It's just a set where where p of v given x1 does not have the largest likelihood. So in this region we make one decoding error. We don't know to which one, but we make one decoding error, and we have essentially a few possibilities. We have the possibility that we make a decoding error to J, and that's the set WMLJ. So that's where the maximum likelihood decoder will output XJ. And then we have the possibility, for instance, in here, this is the region where P of V given Xk is still larger than P of V given Xj. So we have a few possibilities. So if P of V given Xk is larger than P of V given Xj, the maximum likelihood decoder will not decode to Xj because there is one vector that has a higher likelihood. So it may decode to Xj. And only in this red region, P of V given Xj has the highest likelihood. And in this region, the decoder will output Xj. So I hope that's clear. That takes a little bit of processing until this becomes clear. So in this region, it means that the decoder will not decode to Xi because the likelihood of Xj is larger. P of Y given Xj is larger. And it may decode to Xj if this is the largest of all likelihoods. But there may be the case where there is another, some Xk, which has a larger likelihood, and the maximum likelihood decoder will decode to the wrong one. So, and that's the set WMJ. The set WMJ is the set where the decoder will, the maximum likelihood decoder will decode Xj, and this one is a subset of Wj. And this is important because this set is very difficult to analyze because maximum likelihood decoder is a difficult beast. The blue set is quite simple to analyze, so this is why we relate everything to the blue set. Okay, so now we can start calculating the probability that the maximum likelihood decoder decodes to Xj. And that's the sum over all vectors V that are in this red set WMLJ of P of V given X1. That's the probability that we decode to Xj. So, because I said this red set is difficult to analyze, we bound this probability by this set. So in this set, we have a bound, and we sum up over all V's from Wj, which is a larger set, therefore we have an inequality of P of V given X1. Now, in this blue set, we have the following. In the blue set, we have P of V given Xj is larger or equal than P of V given X1. And that means that P of V given Xj divided by P of V given X1 is larger or equal than 1. And this means that we can also put a square root in front, and it will still be larger or equal than 1. So we have a term here that is larger or equal than 1 when we are in this blue set. So we can further bound by multiplying this term by the blue term. Take this blue term, this guy, and we just multiply our equation by the blue term, and we have a further inequality. Smaller or equal than the sum over Vj of P of V given X1 times this blue term. And now we can cancel. So we can cancel this guy, or we can say we put square root here and then cancel this guy. And we end up with this one. So the sum of all v element from wj times the square root of p of v given x1 times p of v given xj. And you can already see the similarity to the Bhattacharya parameter. So next we need to further simplify because we still have not the term that we'd like to. Still have vectors in here that we need to get rid of. We have this wj here that we get rid of. First thing, we're going to get rid of wj. So we see that wj is a subset over w power n. So again, we can do the same trick and we can bound. Because this is a larger set and vj is a subset of w power n. So we have a new bound, pj is smaller or equal than the sum over all v from w power n. And we have the square root of these two guys. Now we use the memorylessness of the channel. So memoryless means that p of v given x1 is equal to the product from L1 to n of p of v L given x L1 and so on. So we just insert this the memorylessness here, then we get the sum over a product, and we get the product over p of vl xl1 times p of vl xjl. So we have the sum over all possible vectors times this product, and now we use the distributive law and to exchange the summation with the product. So instead of summing over all possible vectors, we take the product first and then sum over all possible outcomes v. Then we get the product from the probability of v given x equals 0 times p of v given xlj. Because here we assume that we know that xl1 is equal to 0 because we transmit the all 0 code word. So in order to see how this step works, we can consider a small example. And small example with W. So we have a channel with an output alphabet of size 3, and the possible outputs are alpha, beta, gamma, and n is equal to 2 to keep everything simple. And then we start in reverse. So we start with the product from L equals 1 to 2, and we have the sum over V element from W. And we just insert P of V given x equals 0 times P of V given x equals xj1. And because we don't want to write too much, we define that this is equal to K1. This should be an L, so XLJ. So this is equal to K. Erase. This is equal to KL. We are getting there. This is equal to KLV. So writing this out gives us, this is equal to, I'm going to write here, is equal to the square root of K1 alpha plus the square root of K1 beta plus the square root of K1 gamma times, and now I have the square root of K2 alpha plus the square root of K2 beta plus the square root of K2 gamma. And now it's just applying the distributive law. So I get the square root of k1 alpha plus k2 alpha, or times k2 alpha, plus the square root of k1 alpha times k2 beta, plus the square root of k1 alpha times k2 gamma, plus the square root, I'm going to next line, k1 beta times k2 alpha, plus the square root of k1 beta times k2 beta, plus the square root of k1 beta times k2 gamma, plus square root of k1 gamma times k2 alpha, plus the square root of k1 gamma times k2 beta, plus the square root of k1 gamma times k2 gamma. And we see that this is equal to the sum over all vectors v, element w squared. We have 3 squared elements, so we have 9 possible elements. So it's combinations of alpha, beta, and gamma in the first place, and alpha, beta, gamma in the second place. So it's 9 different summons. And then we multiply from L equals 1 to 2, n equals 2, and we have the square root of k kl vl. And that's the other interpretation. So we can easily, if we have a sum over all possible combinations, then we have the product over all the elements, then we can swap product and the summation by factoring this expression, and essentially we go back. So from the big expression, we factor the common parts of it. That's the idea. So that's what we have. We have the product over the sum over all elements from the output alphabet W, and then we have this term. So now what is this term? So in this term we have 2 possibilities. So the first possibility is if xlj is equal to 0. If xlj is equal to 0, then the following happens. Let's write it down. So xlj is equal to 0. Then we have the sum over all v element from W. Then we have the sum over p of v given x equals 0 squared. Together with the square root, this cancels. So we have the square root that cancels and the square that cancels. And we are left with the sum over all p of v given x equals 0. And that's just equal to 1. Because it's the sum over all v's. So we sum over all the alphabets, so that's equal to 1. Now if x is not equal to 0, this is exactly the definition of the Bhattacharya parameter. So we have b of c in the other case. Okay. So now we can put everything together. So let me put this one on the next slide so that we have it as a reference. This is not what I wanted to do. This is what I wanted to do. So if there's a reference, I can increase the size a little bit. Okay, so sorry for this red cross, that's an artifact. So now we calculate how often we have this case. This case doesn't matter because we multiply once, it doesn't count in the multiplication. So how often do we have this case? We have this case if XL is different from X from 0. Exactly the Hamming weight. So the number of times the second case occurs is exactly equal to the Hamming weight Wxj. So we can say that Pj is upper bounded by the Bhattacharya parameter of W to the power xj. We take the Bhattacharya parameter W times, the remaining times are equal to 1s, so we don't care about those, and so we take it B times. So and that leads us to the probability that the maximum likelihood decoder makes an error. That's PE, that's the error probability. That's equal to the sum over all Pj. And that's the sum from j equals 2 to 2 power k of the Bhattacharya parameter of the weight of xj. So now we have the sum over all code words. How often do we have a code word with weight w? Well, it's given by the weight enumerator. So instead of going over all the code words, we group the ones with the same weights. The weight enumerator AW tells us how often such a code word occurs. And when it occurs, we have a contribution to the sum, which is the Bhattacharya parameter of W to power weight given xj. So this is equal to the sum of AW times Bhattacharya parameter to the power W, or it's the weight enumerator evaluated at the Bhattacharya parameter. And then if we assume that all the code words are equiprobable, this is the error probability of all the code. So that's it. So we have a very simple bound on the Bhattacharya parameter. So what are the implications? So implication is the following. Maximum likelihood decoding error is smaller or equal than AB. And we can write this. So AW is 0 if W is smaller than the minimum distance. So this is A to the power minimum distance times B to the power minimum distance plus A to the power minimum distance plus 1 times B to the power minimum distance plus 1. Now we know the Bhattacharya parameter is between 0 and 1. 0 means we have a very bad channel. 1 means we have a very good channel. So if the Bhattacharya parameter is small, or if it's between 0 and 1, this term will dominate the sum. Because this one will get, if we increase the exponent, the smaller the term gets. We always get smaller, 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 because we have a number between 0 and 1 that we exponent, where we take the exponent, and that makes the number smaller and smaller and smaller. So if the Bhattacharya parameter is small enough, this term dominates. And in this case, the minimum distance dominates the decoding performance. We can make this bound small if we push, or we can make the maximum likelihood decoding performance small if we push this number down. How can we push this number? We can push this number if we make dmin large. Making a larger minimum distance will lead to a small maximum likelihood decoding performance. That's what you should take away from here. And so this is one of the reasons the minimum distance is important. And minimum distance is not only important, it was very important in classical coding, but these weights are also important. So what can happen is that the minimum distance is very small, but if this A is very small as well, then this term still doesn't have a contribution. So modern coding also focuses on A, so to make the A small if the min is small. We can tolerate a small minimum distance, but if this guy is small, then the contribution will be small as well. So we can have a minimum distance that is small if A is small, so we have a good weight enumerator. That means maximum likelihood decoding performance can also be pushed down. And therefore, we like to have small values of AJ. I mean, what we have in total is the sum over, we cannot freely choose because the sum over all AJ, J from 1 to n, is equal to 2 power k minus 1 is equal to m minus 1. So we cannot freely choose because we have always constrained that the sum of the weighted enumerator must be constant. It's not something that we can really select. So if you like to play around a little bit with this bound, you can take a look at maximum likelihood decoding and this bound in a small MATLAB script that you find on the GitHub server. So with this, we are at the end of the second chapter, and in the next chapter, we're going to take a look at low-density parity check codes.